Chapter 1: Sets and Functions, Basic Mathematical Foundations for Machine Learning. Hello everyone. Welcome to the second week of the Machine Learning Foundations course. This week we will look at the basic mathematical tools that will be required for the rest of the course. I have titled this week Calculus because calculus forms the majority of the material. Much of it overlaps with the later part of the Mathematics 2 course that you may already have completed. However, our focus will be somewhat different. Rather than emphasizing symbolic manipulation, we will spend more time looking at geometric intuition and graphical interpretations, which are particularly useful in data science and machine learning. Let me briefly outline the topics we will cover. We will begin with some basic sets and functions, along with a notation that we will use throughout the course. After that, we will look at a few fundamental ideas of mathematical logic and how they are represented symbolically. Finally, we will discuss different ways of visualizing functions graphically. Basic sets: there are several sets that we will use repeatedly throughout the course. The first set is the set of all real numbers. Next is the set of all non-negative real numbers, including 0. We also have the set of integers and the set of all non-negative integers, including 0. These four sets will appear frequently. Another important type of set is an interval. A closed interval from A to B contains all real numbers between A and B, including both endpoints. A closed interval can therefore be described as the set of all real numbers x such that r is less than or equal to x, and x is less than or equal to b. We also have the open interval from A to B, which consists of all real numbers x such that r is less than x, and x is less than b. The only difference is that the endpoints A and B are excluded. Cartesian products: any of these sets can be combined with itself multiple times using a Cartesian product. For example, the Cartesian product of the real numbers with itself d times means the set of all d-dimensional vectors. An example element of three-dimensional real space would be the vector 1, 2, 3. More generally, we can take the Cartesian product of almost any set. For example, the interval from A to B raised to the power d represents the set of all d-dimensional vectors whose coordinates lie between A and B. Equivalently, this is the set of all vectors x in d-dimensional real space such that every coordinate x sub I belongs to the interval from A to B. These are some of the basic sets that we will use throughout the course. Metric spaces: the next mathematical object we will study is a metric space. A metric space is simply a set equipped with an additional structure called a distance function. A distance function takes two elements of the set and returns the distance between them. The default metric space for most of this course will be d-dimensional real space together with the Euclidean distance. The Euclidean distance between vectors x and y is defined as the norm of x minus y. Written explicitly, this is the square root of x sub 1 minus y sub 1, all squared, plus x sub 2 minus y sub 2, all squared, and so on up to x sub d minus y sub d, all squared. This is the standard Euclidean distance that you are already familiar with from geometry. Open and closed balls: an important concept associated with metric spaces is a ball. Given a point x and a positive radius epsilon, the open ball centered at x with radius epsilon is the set of all points y, whose distance from x is strictly less than epsilon. The closed ball is similar except that points whose distance is exactly equal to epsilon are also included. So the only difference between an open ball and a closed ball is whether the boundary is included. For example, suppose we are in two-dimensional space and the center point is the vector 1, 1. If we draw a circle of radius 0.5 around a point, the interior of the circle is the open ball. The interior together with the boundary is the closed ball. Balls will play a central role in analysis and calculus. Sets and logic: let us now review some basic ideas from set theory and logic. Suppose we have a universe B containing two sets A and B. There are several standard operations we can perform. The first is the union of A and B. The union consists of all elements that belong to A or B. The second is the intersection of A and B. The intersection consists of all elements that belong to both sets. We also have the complement of a set. The complement of A consists of all elements in the universe that are not contained in A. Another notation for the complement of A is B set difference A. The set difference operation denotes elements that belong to one set, but not another. De Morgan's law's one of the most important identities involving sets is De Morgan's law. The first law states that the complement of a union B is equal to the intersection of the complement of A and the complement of B. The second law states that the complement of the intersection of A and B is equal to the union of the complement of A and the complement of B. These identities are very easy to understand using Venn diagrams. The first law says that elements outside both A and B are exactly the elements that are outside A and also outside B. The second law says that everything except the overlap of A and B is obtained by taking all points outside A together with all points outside B. Example of De Morgan's law: let the universe be the closed interval from 0 to 10. Suppose A is the closed interval from 2 to 5 and B is the closed interval from 4 to 7. Then the union of A and B is the closed interval from 2 to 7. The intersection of A and B is a closed interval from 4 to 5. Now consider the complement of the union. This consists of everything in the universe except the interval from 2 to 7. Therefore, it is the interval from 0 to 2 excluding 2, union the interval from 7 to 10 excluding 7. If we compute the complement of A and the complement of B separately and then intersect them, we obtain exactly the same result. This verifies De Morgan's law. Logic symbols. Several logic symbols will appear throughout the course. The upside down A symbol means for all. The upside down E symbol means there exists. A single arrow means implies. A double arrow means if and only if, or equivalently, logically equivalent. For example, if A and B are statements, then A implies B means that whenever A is true, B must also be true. Or if and only if B means that A implies B and B implies A. Sequences. We now come to one of the most important concepts in analysis. A sequence is simply an ordered collection of elements. Consider the sequence defined by x sub n equals 1 plus 4 divided by 2 raised to the power n, 3 minus 4 divided by 2 raised to the power n. Each term is a two-dimensional vector. When n equals 1, we obtain 3, 1. When n equals 2, we obtain 2, 2. As n becomes larger and larger, 4 divided by 2 raised to the power n becomes smaller and smaller. Eventually, it becomes arbitrarily close to 0. As a result, the sequence approaches the point 1, 3. The points move closer and closer to this location. A non-convergent sequence. Now consider another sequence. X sub n equals cosine of n divided by 2, sine of n divided by 2. The first few points move around the unit circle. Because sine and cosine are periodic, the sequence keeps cycling through the same locations. It never settles down near a single point. Therefore, the sequence does not converge. This contrasts with the previous example where the points eventually approached a fixed location. Convergence. We now define convergence formally. We say that the limit of x sub n as n approaches infinity is x bar if the following condition holds. For every positive epsilon, there exists an integer n such that whenever n is greater than or equal to that value, the point x sub n lies inside the open ball centered at x bar with radius epsilon. Let us interpret this carefully. The phrase for every epsilon means that you may choose any radius you like, no matter how small. You might choose 0.1, 0.01, 0.001, 0.0001, or an even smaller radius. The condition says that eventually every term of the sequence will remain inside that ball forever. For the first sequence, this condition is satisfied with x bar equal to 1, 3. For the second sequence, it is not satisfied for any point. The sequence keeps moving and never stays inside any sufficiently small ball permanently. Therefore, the first sequence converges. The second sequence does not converge. You may also see convergence written as x sub n approaches x bar. These statements are equivalent. Exercise: consider the following sequences. First, x sub n equals 1 plus n. Does this sequence converge? Second, x sub n equals 1 divided by 2 raised to the power n multiplied by cosine of n divided by 2, 1 divided by 2 raised to the power n multiplied by sine of n divided by 2. This resembles the earlier circular sequence, but now the radius shrinks exponentially. Does it converge? Third, x sub n equals 1 divided by 2 raised to the power n multiplied by cosine of n divided by 2, sine of n divided by 2. Only the first coordinate shrinks. Does the sequence converge? Determine whether each sequence has a limit, and, if so, find that limit. Vector spaces. The next fundamental object is a vector space. A vector space is a set together with operations that satisfy several properties. The most important property is closure under linear combinations. Suppose U and V belong to a vector space. Suppose alpha and beta are arbitrary real numbers. Then alpha multiplied by U plus beta multiplied by V must also belong to the vector space. In words, any linear combination of vectors in the space must remain inside this space. The most important example for us is d-dimensional real space. If you add two d-dimensional vectors, you obtain another d-dimensional vector. If you multiply a d-dimensional vector by a scalar, the result is still d-dimensional. Therefore, d-dimensional real space is a vector space. Dot products and norms. A vector space is often equipped with a dot product. Given vectors x and y, the dot product is defined as the sum from I equals 1 to d of x sub I multiplied by y sub I. The squared norm of a vector x is obtained by taking the dot product of x with itself. Therefore, the norm squared equals the sum from I equals 1 to d of x sub I squared. The norm measures the length of a vector. Orthogonality. Two vectors are said to be orthogonal, or perpendicular, if their dot product is 0. In other words, the sum of x sub I multiplied by y sub I over all coordinates is equal to 0. Orthogonality will appear frequently in linear algebra and machine learning. Functions. We now turn to functions. A function is simply a mapping from one set to another. If a function maps a set A into a set B, then A is called the domain and B is called the codomain. A real-valued function is a function whose codomain is the real numbers. We will mostly work with real-valued functions. A one-dimensional function maps the real numbers to the real numbers. A multivariable function maps two-dimensional real space into the real numbers. Graphs of functions. Given a function from d-dimensional real space into the real numbers, we can define its graph. The graph consists of all pairs consisting of x and f of x, where x belongs to d-dimensional real space. Because x has d coordinates and f of x contributes one additional coordinate, the graph lives in d plus 1 dimensions. Visualizing one-dimensional functions. For a one-dimensional function such as f of x equals x squared, visualization is straightforward. We place x on the horizontal axis and f of x on the vertical axis. Plotting all such points produces the familiar parabola. Visualizing two-dimensional functions. Things become more challenging when the function maps two-dimensional real space into the real numbers. The graph now lives in 3 dimensions. Since paper and computer screens are essentially two-dimensional, visualizing such functions directly is difficult. The standard solution is a contour plot. Consider the function f of x equals x sub 1 plus x sub 2. Choose a collection of output values such as -1, 0, and 1. For each value, solve the equation f of x equals that value. For example, f of x equals -1 gives x sub 1 equals negative x sub 2 minus 1. This produces a straight line. Similarly, setting the function equal to 0 or 1 produces other lines. Each line consists of points where the function has the same value. Such lines are called contours. You may have encountered similar ideas in geography through isotherms, which connect points of equal temperature, or isobars, which connect points of equal pressure. Those are contour plots. Another contour example, consider f of x equals x sub 1 multiplied by x sub 2. The contours are no longer straight lines. For example, the contour corresponding to 10 consists of all points where x sub 1 multiplied by x sub 2 equals 10. The contour corresponding to -10 consists of all points where x sub 1 multiplied by x sub 2 equals -10. These contours reveal the structure of the function. Heat maps. Sometimes we add color to contour plots. High values may be shown in bright colors, while low values may be shown in darker colors. If we draw sufficiently many contours and color them appropriately, the picture becomes a heat map. A heat map contains more detailed information about function values, while a contour plot often makes the geometric structure easier to see. Circular contours. As a final example, consider f of x sub 1, x sub 2 equals x sub 1 squared plus x sub 2 squared. The contours of this function are circles centered at the origin. The contour plot clearly shows these circles, and the heat map also displays the same circular structure through color variation. With that, we conclude the basic setup, notation, logical concepts, and visualization techniques that will be used throughout the remainder of this week and throughout the rest of the course.
Here is the complete, expanded version without any bold formatting, just plain text for a clean, audio-friendly transcript. Let's continue our discussion of machine learning foundations. Today, we're building on what we started earlier this week, a brief but thorough recap of univariate calculus. Most of these concepts come from your earlier math courses, Math 1 or Math 2, but they deserve repeating because they'll show up repeatedly throughout this course, especially when we talk about optimization, gradient descent, and loss functions. We'll begin with continuity, then move on to differentiability, and finally interpret the derivative geometrically. Throughout this module, we'll work with real-valued functions of a single real variable. That is, functions that map a real number to a real number. We write this as f from R to R. Continuity at a point. Definition. We say that a function f from R to R is continuous at a point x star in R if the following holds. For every sequence of inputs that converges to x star, the corresponding sequence of outputs converges to f of x star. Let's write that more formally. Let x1, x2, x3, and so on be any sequence such that the limit as I goes to infinity of xi equals x star. Then we require that the limit as I goes to infinity of f of xi equals f of x star. In a more compact notation, we say that the limit as x approaches x star of f of x equals f of x star. That is the statement for a function being continuous at a given point x star. And we say a function is continuous overall if it is continuous at every point in its domain. Example 1. A continuous function. Take f of x equals x squared. Let's test whether this is continuous at x star equals 2. According to the definition, we need to pick any sequence that converges to 2, and then show that the outputs converge to f of 2, which is 4. For instance, consider the sequence 3, 2.5, 2.25, 2.125, and so on. This clearly converges to 2. Now look at the corresponding outputs, 9, 6.25, 5.0625, 4.5156, and so on. You can see that as the inputs get closer and closer to 2, the outputs get closer and closer to 4. So for this particular sequence, it works. But the definition requires it for every sequence, not just one. However, because x squared is a polynomial, we know this holds for all sequences. We just demonstrated it for one representative example. So f of x equals x squared is continuous at x equals 2. In fact, it's continuous everywhere, but this argument only proves it for that specific point. Example 2, a discontinuous function. Now consider the sine function, often written as sgn of x. It is defined as follows: f of x equals -1 if x is less than 0, f of x equals 0 if x equals 0, and f of x equals +1 if x is greater than 0. Let's test continuity at x star equals 0. According to the definition, every sequence converging to 0 must produce outputs that converge to f of 0, which is 0. Take the sequence xi equals 1, 1/2, 1/4, 1/8, and so on. This converges to 0. What are the outputs? F of 1 is 1, f of 1/2 is 1, f of 1/4 is 1, and so on. So the output sequence is just 1, 1, 1, and so on, which converges to 1. That already violates the definition because we need it to converge to f of 0, which is 0, not to 1. But let's go further, to really emphasize the for all sequences part. Consider another sequence, xi equals -1, -1/2, -1/4, -1/8, and so on. This also converges to 0. But now the outputs are f of -1, which is -1, f of -1/2 is -1, f of -1/4 is -1, and so on. So this output sequence converges to -1. So we have two sequences, both converging to 0, but one gives outputs converging to 1, and the other gives outputs converging to -1. Neither equals f of 0, which is 0. Therefore, the definition fails. The function is not continuous at 0. Now here's an important subtlety that the definition highlights. What if we had defined f of 0 differently? Suppose we had set f of 0 equal to 1 instead of 0. Then the first sequence would satisfy the condition because outputs go to 1, and f of 0 is 1. But the second sequence would still give outputs converging to -1, which is not equal to 1. So the definition would still fail. Similarly, if we set f of 0 to -1, the second sequence would work, but the first wouldn't. If we set f of 0 to anything else, both would fail. The point is, no matter what value you assign at that single point, you cannot satisfy the for all sequences requirement because the left-hand limit and right-hand limit disagree. That's why we call this a discontinuity at 0. And since it fails at even one point, we call the function as a whole discontinuous. Example 3, another discontinuous function. Take f of x equals 1 over x. Is this continuous everywhere on the real line? No, because it's not even defined at 0. But could we define f of 0 to be something and make it continuous? Let's test. Consider the sequence xi equals 1, 1/2, 1/4, 1/8, and so on, which converges to 0. The outputs are 1, 2, 4, 8, 16, and so on, which grow without bound. They do not converge to any finite number. So no matter what value we assign to f of 0, this output sequence will never converge to it. Therefore, 1 over x is not continuous on the whole real line. However, we can say that 1 over x is continuous if we restrict the domain to, say, positive numbers only. For example, on the closed interval from 1 to 7, it behaves nicely. But the moment the domain includes 0, continuity fails. Example 4, yet another discontinuous function. Consider f of x equals cosine of 1 over x for x not equal to 0. What happens as x approaches 0? Take the same sequence xi equals 1, 1/2, 1/4, 1/8, and so on. The outputs are cosine of 1, cosine of 2, cosine of 4, cosine of 8, cosine of 16, and so on. These values oscillate between -1 and 1 and do not settle to any single number. So the sequence of outputs does not converge. Therefore, the function is not continuous at 0. Again, no matter what value we assign to f of 0, the sequence fails to converge to it. So this is another classic example of a discontinuity. Differentiability at a point definition. Now we move to differentiability. The definition is similar in spirit to continuity. A function f from R to R is differentiable at a point x star in R if the following limit exists. The limit as x approaches x star of x minus f of x star divided by x minus x star. When we say the limit exists, we mean that it converges to some finite real number. If it does exist, that particular value is called the derivative of f at x star, and we denote it by f prime of x star. There is an equivalent formulation that is often more convenient. Let h equal x minus x star. Then as x approaches x star, h approaches 0. So we can rewrite the derivative as the limit as h approaches 0 of f of x star plus h minus f of x star, all divided by h. These two expressions are exactly the same. The second one just shifts the point of interest to 0, which makes geometric interpretation easier, as we'll see shortly. Continuity is necessary, but not sufficient for differentiability. Here's an important logical connection. If a function is not continuous at x star, it cannot be differentiable there. Why? Because differentiability requires the difference quotient to have a limit, and that limit implicitly requires the numerator to go to 0, which is exactly continuity. So we can say, if f is not continuous at x star, then f is not differentiable at x star. However, the converse is false. A function can be continuous at a point, but still fail to be differentiable there. That is, continuity does not imply differentiability. Example, continuous, but not differentiable. The standard example is the absolute value function. F of x equals the absolute value of x. It is continuous everywhere, including at 0. But let's test differentiability at x star equals 0. We need to check whether the limit of f of x minus f of 0 divided by x minus 0 exists as x approaches 0. Take the sequence xi equals 1, 1/2, 1/4, 1/8, and so on, which converges to 0. For each term, the difference quotient is as follows. For x equals 1, we have 1 minus 0 divided by 1 minus 0, which is 1. For x equals 1/2, we have 1/2 minus 0 divided by 1/2 minus 0, which is 1. For x equals 1/4, we have 1/4 minus 0 divided by 1/4 minus 0, which is 1. So the sequence of quotients converges to 1. Now take a different sequence that also converges to 0, xi equals -1, -1/2, -1/4, -1/8, and so on. For each term, the quotient is as follows. For x equals -1, we have 1 minus 0 divided by -1 minus 0, which is -1. For x equals -1/2, we have 1/2 minus 0 divided by -1/2 minus 0, which is -1. For x equals -1/4, we have 1/4 minus 0 divided by -1/4 minus 0, which is -1. So the sequence of quotients converges to -1. We have two sequences, both converging to 0, but the difference quotients converge to two different values, 1 and -1. Therefore, the limit does not exist. Hence, f of x equals absolute value of x is not differentiable at 0, even though it is continuous there. Piecewise examples, step by step. Let's work through two piecewise functions to see how continuity and differentiability interact. Example A. Define f of x equals 4x plus 2 if x is greater than or equal to 2, and f of x equals 2x plus 8 if x is less than 2. First, check continuity at x equals 2. From the right, meaning x approaching 2 from above, for example 2.1, 2.01, and so on, the limit is 4 times 2 plus 2, which is 10. From the left, meaning x approaching 2 from below, for example 1.9, 1.99, and so on, the limit is 2 times 2 plus 8, which is 12. Since 10 does not equal 12, the two one-sided limits disagree. Therefore, the function is not continuous at 2. And since it's not continuous, it cannot be differentiable there. So we're done. No need to check the difference quotient. Example B. Now define f of x equals 4x plus 2 if x is greater than or equal to 2, and f of x equals 2x plus 6 if x is less than 2. Check continuity at x equals 2. From the right, we get 4 times 2 plus 2, which is 10. From the left, we get 2 times 2 plus 6, which is 10. They match, so the function is continuous at 2. Now check differentiability. We'll use the one-sided limits of the difference quotient. From the right, for x greater than 2 approaching 2, the quotient is 4x plus 2 minus the quantity 4 times 2 plus 2, all divided by x minus 2. That simplifies to 4x plus 2 minus 10 over x minus 2, which is 4x minus 8 over x minus 2, which simplifies to 4 for all x not equal to 2. So the right-hand limit is 4. From the left, for x less than 2 approaching 2, the quotient is 2x plus 6 minus the quantity 2 times 2 plus 6, all divided by x minus 2. That simplifies to 2x plus 6 minus 10 over x minus 2, which is 2x minus 4 over x minus 2, which simplifies to 2 for all x not equal to 2. So the left-hand limit is 2. Since 4 does not equal 2, the two one-sided limits of the difference quotient disagree. Therefore, the overall limit does not exist, and the function is not differentiable at 2, even though it is continuous there. This reinforces the point that continuity is necessary, but not sufficient for differentiability. Geometric interpretation of the derivative detailed. Now let's build an intuitive picture of what the derivative represents. We'll use the h form of the definition. F prime of x star equals the limit as h approaches 0 of f of x star plus h minus f of x star, all divided by h. Imagine the graph of the function. Pick a point on the curve x star, f of x star. Now choose a small positive step h. For example, start with h equals 1. The point x star plus 1, f of x star plus 1 is another point on the curve. Draw a straight line through these 2 points. That's called a secant line. The slope of that secant line is exactly the ratio f of x star plus 1 minus f of x star divided by 1, which matches the expression in the numerator. Now reduce h to 1/2. Now the secant line goes through x star, f of x star, and x star plus 1/2, f of x star plus 1/2. Its slope is f of x star plus 1/2 minus f of x star, divided by 1/2. The secant line is closer to the curve near x star than the previous one. Reduce h further to 1/4, then 1/8, and so on. Each time, the secant line gets closer and closer to the curve in a small neighbourhood around x star. If you imagine zooming in on the graph at that point, the curve begins to look more and more like a straight line. In the limit as h approaches 0, the secant line converges to a unique line that just touches the curve at that single point. That's the tangent line. The slope of that tangent line is exactly the derivative, f prime of x star. So geometrically, the derivative is the slope of the tangent line to the function at that point. Equivalently, it tells us how steep the function is at that exact location. It tells us how much f of x changes for an infinitesimally small change in x. This tangent line also gives us the best linear approximation to the function near x star. That approximation viewpoint is extremely important in optimization, because many machine learning algorithms like gradient descent, replace complicated functions with their linear approximations to find minima. We'll explore that formally in the next module, where we connect derivatives to linear approximations and tailor expansions. Summary and transition. To wrap up, continuity requires that for every sequence approaching a point, the outputs approach the function's value at that point. Differentiability requires that the difference quotient has a single, well-defined limit, independent of how we approach the point. Continuity is necessary for differentiability, but not sufficient. The absolute value function is the classic counterexample. Geometrically, the derivative gives the slope of the tangent line and provides a linear approximation to the function. Next time, we'll formalize that approximation idea and see how derivatives help us optimize functions, which is a core tool in training machine learning models. Thank you for listening, and I'll see you in the next module. Hello, everyone, and welcome to another lecture of Machine Learning Foundations. We will continue with the univariate calculus ideas that we began last class. In this session, we will mainly focus on the derivative and its link to what are called linear approximations. Let us consider a differentiable function from the real numbers to the real numbers. So, let f from r to r be a differentiable function. What is the definition of the derivative? Well, f prime of x star is equal to the limit as x approaches x star of x minus f of x star, divided by x minus x star. That is the formal definition we established earlier. Now, we do have a limit term here, so we cannot directly multiply both sides by x minus x star and move things around arbitrarily. But let us assume that x is approximately equal to x star. That is, we are in a regime where x is very close to x star. In that case, the limit condition is essentially satisfied. So we can say that f of x star is approximately equal to f of x minus f of x star, divided by x minus x star, but only in the neighbourhood around x equals x star. Only then can we remove the limit statement without violating the logic. Once we have that, we can rearrange the terms and write an alternative expression. F of x is approximately equal to f of x star plus f prime of x star times x minus x star. So, f prime of x star is approximately equal to the difference quotient around x equals x star, which means that f of x is approximately equal to f of x star plus f prime of x star times x minus x star. This is also true only when x is close to x star. This is called a linear approximation. You can view the left-hand side as a function of x. The right-hand side can also be viewed as a function of x. You can treat x star and f prime of x star as constants. F of x star is a constant. F prime of x star is also a constant. The entire expression can be seen as a function of x. We're going to denote that by L sub x star of f evaluated at the point x. So L sub x star of f of x is that whole linear expression. What the approximately equal to statement says is that f of x is approximately equal to L sub x star of f evaluated at x, around x equals x star. This is the key idea. The key expression in essentially first-order calculus. F of x can be approximated by f of x star plus f prime of x star times x minus x star, around x equals x star. This is the key approximation idea that we will be using for a major part of machine learning. So, what does this mean for us? Let us give a graphical illustration of this. Consider the simple function f of x equals x squared, which we know to be differentiable. Let us pick x star equal to 1. Consider the point x star, f of x star. What is f prime of x star? F prime of x star is simply equal to 2. That follows from basic calculus. F of x is x squared, f prime of x is 2x, so f prime of 1 is 2. Now we can write down what the linear approximation actually is. What is it? L sub x star of f of x is simply f of x star plus f prime of x star times x minus x star. Plugging in our values, x star is 1, so f of x star is 1 squared, which is 1 f prime of x star is 2. So we get 1 plus 2 times x minus 1. That simplifies to 1 plus 2x minus 2, which is 2x minus 1. So what we're saying is that the linear approximation of f around x equals 1 is the function 2x minus 1. This is valid around x equal to 1. Graphically, the red line corresponds to the graph of 2x minus 1. And you can see that this particular graph is an approximation to the black curve, which corresponds to x squared, around x star equals 1. At x star equals 1, it exactly touches the curve. It is exact at that point. The farther your x moves from x star, the worse your approximation becomes. Around x equals x star, your red line and black line coincide quite well. That is the reason why it is called an approximation. As your x moves farther and farther away from x star, it becomes a worse approximation. For example, at x equals 2, we can see that there is actually a gap between f of x and L sub x star of f evaluated at x. That point on the red line corresponds to x, L sub x star of f evaluated at x. So that is the reason why I'm saying that L sub x star of f is an approximation of f around x equals x star. That is what we mean by saying that L sub x star of f is a linear approximation. And why is it a linear approximation? You can see that the graph of L sub x star of f is a straight line. Why is that? Because in our example, 2x minus 1 is a linear function of x. The coefficient of x is constant, so it is the equation of a straight line. In general, this is also true because L sub x star of f viewed as a function of x has coefficient f prime of x star, which is a constant. We have f of x star as a constant, and f prime of x star times minus x star is also a constant. So the whole expression simplifies to a constant times x plus another constant. That is the reason why this is called a linear function. And this is an approximation of f around x equals x star. So that is about linear approximations. You would have also seen another interpretation of linear approximation via what are called tangent lines. A tangent is a geometric object, while a linear approximation is a functional object. What is a tangent? Loosely speaking, a line is a tangent to a set if that line touches the set. I am not going to define touching in a formal sense because that is too much work, but intuitively, in this case, you can see that the red line, which corresponds to the graph of the linear approximation of f around x star, is a tangent to the graph of f. Or in other words, I will write it in a formal way, the graph of L sub x star of f, which is also a function, is a subset of r squared in the case of functions from R to R. That graph is a tangent to the graph of f at the point x star, f of x star. This point is where the two sets touch each other. That is the definition of a tangent line. The graph of a linear approximation forms a tangent line to the graph of the function. Now that we have the basics of linear approximations and tangent lines, we can see some examples. The first example is perhaps the most famous one. Give the linear approximation of f of x equals sine x around x star equals 0. To do that, you need f prime of x. F prime of x is simply cosine x. F prime of x star, which is 0, is cosine of 0, which is 1. And f of x star, which is sine of 0, is 0. With these three facts put together, we can say that f of x is approximately equal to f of x star plus f prime of x star times x minus x star. What is that? That is 0 plus 1 times x minus 0, which is simply x. And when is this valid? This is valid around x equals 0, when x is close to 0. So this says that sine x is approximately equal to x, if x is approximately equal to 0. This is the famous limit of sine theta over theta equals 1 that you would have derived in school. Let us do one more classic example. Let f of x equal e to the power x. I want the linear approximation of this function around x star equals 0. In this case, what would e to the power x be approximately equal to? It is approximately equal to e to the power 0, which is 1, plus x minus 0 times f prime of 0. F prime of x is e to the x, so f prime of 0 is 1. So e to the x is approximately equal to 1 plus x around x equals 0. I'm going to highlight the fact that e to the x approximately 1 plus x is true only around x equal to 0. Similarly, a few more classic examples. Let us do the natural logarithm of 1 plus x around x star equals 0. Let f of x equal log of 1 plus x. What is f prime of x? F prime of x is 1 divided by 1 plus x. So f prime of x star is f prime of 0, which is 1. And f of x star is f of 0, which is log of 1, which is 0. We can put all that together and say log of 1 plus x is approximately equal to log of 1, which is 0, plus f prime of x star, which is 1, times x minus 0. So log of 1 plus x is approximately equal to x around x equals 0. We will do one more example. Let f of x equal 1 plus x raised to the power r, where r is some integer, say 2, or 3, or 7. It does not matter. We want to approximate 1 plus x to the power r round x equals 0. What is f of x star? F of 0 is 1 to the power r, which is 1. F prime of x in general is r times 1 plus x to the power r minus 1. And f prime of x star, in particular, is f prime of 0, which is r times 1 to the power r minus 1, which is just r. We can put all of that together and say that 1 plus x to the power r is approximately equal to 1 plus r times x minus 0, which is just 1 plus rx. And this is also valid around x equal to 0. So this should give you an idea that a lot of calculus makes approximations very easy to write down. We have e to the x is approximately 1 plus x around x equals 0. Log of 1 plus x is approximately x around x equals 0, and so on. You can generally apply this to any function that you have. If you want an approximation that is valid around a particular point x star, you can just use f of x star plus f prime of x star times x minus x star. The advantage of the linear approximation is that it is a much simpler object than the original function. And this is going to be the key idea that drives most of optimization. Let us apply this particular idea to a simple question. Here is an exercise. Which of the 4 options is closest to 0.99 to the power 7? The 4 options are, let us say, 0.95, 0.93, 0.91, and 0.9. You have 4 options here. The exercise is to find which of these 4 options is closest to 0.99 to the power 7. None of these are exact, but the question is which is closest. So 0.99 to the power 7 should immediately make you think of 1 plus x to the power 7, where x is equal to minus 0.01. And minus 0.01 is close enough to 0 that you can apply a linear approximation. That means 0.99 to the power 7 is very easily approximated by 1 plus 7 times minus 0.01, which is 1 minus 0.07, which is 0.93. So 0.93 is a good approximation. You can immediately get an answer of 0.93 for a complex thing like 0.99 to the power 7, based on the linear approximation. Intuitively, it makes sense. 0.99 to the power 7 essentially corresponds to 1% decay of, let us say, your money in a bank every year. What happens after 7 years? How much money would remain in the bank? A first approximation would say, well, there's compound interest happening, but it is only 7 years, a small enough number of years, and 1% is a small percentage, so I can say that after 7 years I would have lost 7%, which means I will be left with 0.93 of my original money. Linear approximation essentially makes this a more formal way. By approximating compound interest with simple interest, what you're doing is essentially using a linear approximation. And this is a valid approximation as long as the rate of interest is small enough. In this case, 1% is a small enough rate that you can do this validly. Later, we will see that this is not always valid. In fact, if instead of a 1% loss we had a 10% loss, this would no longer be true. That is for the same reason why L sub x star of f is only an approximation of f around x equals x star. As you move farther and farther away from x star, where L sub x star of f evaluated at x is not going to be exactly equal to f of x. It is going to be different. With that, we have come to the end of derivatives and linear approximations. Next, we will have a look at some slightly more advanced rules and applications of the derivative and linear approximations. Thank you.
Now we will take a look at some applications or advanced rules. We will not go into great detail, but these will still be useful for understanding the basic terms we have been discussing. The first question that comes to mind is, why linear approximations? They're fine, but what is so special about them? We have been approximating f of x by the linear approximation of f around some point x star. That is what we have been doing. But you could argue that there is nothing special about linear functions, and you can go higher. In fact, you could do that, and that is the fundamental idea behind higher order approximations. The linear approximation would simply say that f of x is approximately equal to f of x star plus f prime of x star times x minus x star. That would be the linear approximation. But you could go to a higher order approximation and have a quadratic approximation instead, which would say that f of x is approximately equal to f of x star plus f prime of x star times x minus x star plus 1/2 times f double prime of x star times x minus x star. The whole thing squared. This is called a quadratic approximation. Both of these are valid around x approximately equal to x star. The first expression is the linear approximation. The second expression is the quadratic approximation. Both are approximations, but the second is a better approximation than the first. However, it comes at a cost. It is significantly more complex, with a quadratic term here as opposed to just a linear term. For a special class of functions, quadratic approximations are exactly equal to the function itself. The classic case for that is f of x equals x squared itself. Let us take example 1, f of x equals x squared. In that case, f prime of x is 2x, and f double prime of x is simply the derivative of the derivative, which is 2. Let us pick any x star. It does not matter. X squared is approximately equal to x star squared plus f prime of x star, which is 2x star, times x minus x star, plus 1/2 times 2 times x minus x star, the whole thing squared. That simplifies to exactly x squared. So you end up with the approximation being exactly equal to the function, because the function itself is quadratic in nature. A quadratic approximation is going to give the original function itself. That is not true for all functions. For example, you could have e to the power x instead. If you approximated e to the power x around x star equal to 0, e to the power x would be approximately equal to e to the power 0 plus e to the power 0 times x minus x star plus 1/2 times e to the power 0 times x minus x star, the whole thing squared. Since x star is 0, that is 1 plus x squared over 2. If you are familiar with the Taylor series, that is exactly what it is. The linear approximation truncates the Taylor series at the linear term. The quadratic approximation truncates the Taylor series at the quadratic term. You could in principle go up to cubic, quartic, quintic, and so on. In most machine learning applications, you will stop at the linear approximation. There are certain situations where you will go to the quadratic approximation, but in no practical scenario will you ever go beyond quadratic approximations. Here is a couple of examples where quadratic approximation will actually be useful. Here is an exercise question, which is closest to 1.1 to the power 7. The four options are 1.7, 1.9, 2.1, and 2.3. If you did a linear approximation, you know that 1.1 to the power 7 is simply 1 plus 7 times 0.1, which is 1.7. That makes the compound interest, simple interest logic clear. 1.1 to the power 7 means that every year your money grows by 10%. So after 7 years, if you use simple interest, you would just get 1.7. But that is not what we are asking. We are asking for compound interest. With 7 years and 10%, simple interest is no longer a good approximation of compound interest. In fact, you would expect more. You can get that using a quadratic approximation. The linear approximation would give you 1.7, and the truth is, you can compute the growth using a calculator. What does a quadratic approximation give you? We will compute that now. We have f of x equals 1 plus x to the power 7. F prime of x is 7 times 1 plus x to the power 6. F double prime of x is 42 times 1 plus x to the power 5. We want to approximate f of x around x equals 0 and evaluate it at 0.1. So f of 0.1 is approximately equal to 1 plus f prime of 0. What is f prime of 0? F prime of x is that expression. F prime of 0 is 7. F double prime of 0 is 42. So we get 1 plus f prime of 0 times x minus x star, which is 1 plus 7 times 0.1, plus 1/2 times 42 times 0.1, the whole thing squared. That is 0.01. This is the reason why you can ignore the quadratic term in a lot of cases, because 0.01 is negligible when compared to 0.1. But in this case, it cannot be ignored. If you do the calculation, you actually get 1.91 as your second-order approximation, which is much closer to the truth than the simple first-order approximation of 1.7. So here is an example situation where the second-order approximation gives you much closer results to the truth than the first-order approximation. With that, we move to the next advanced application. The higher-order approximation or quadratic approximation is simply a detour to show that higher-order approximations can exist and might be useful. But for most situations, we will not be bothering with higher-order approximations, and we will just stick to the linear approximation, which is what we will be doing for the rest of the course as well. Now we will come to the product rule, which you are all familiar with. But we will do that from the point of view of linear approximations. Let f of x equal g of x times h of x. Note that right now we are working with all one-dimensional functions, which are functions from reals to reals. Let us consider f of x, which is g of x times h of x. Now you want to know the derivative of f with respect to x. You know the product rule already, but let us try to get to the product rule using the idea of linear approximations. F prime of x is what we want. Now we will do a linear approximation of f, but we will do linear approximations of g and h separately. Let us pick x star equal to 0 for now. You can pick any x star, but life will be easier if we just pick x star equal to 0. G of x is approximately g of 0 plus x times g prime of 0. That is simply the linear approximation of d around x star equal to 0. H of x would be h of 0 plus x times h prime of 0. Now multiply these two approximations together. That gives g of 0 times h of 0 plus x times the quantity g prime of 0 times h of 0 plus h prime of 0 times g of 0 plus an x squared term, which is g prime of 0 times h prime of 0. We started with linear approximations of both terms, but when we multiplied them, we ended up with a quadratic term. So if we want a new linear approximation, we can just ignore the quadratic term. That means that our linear approximation L of f is simply g of 0 times h of 0, which is exactly f of 0, plus x times f prime of 0. Matching terms, we get that f prime of 0 is exactly equal to g prime of 0 times h of 0 plus h prime of 0 times g of 0. This is the product rule, which we derived from first principles based on the idea of linear approximations coming from derivatives. We did a linear approximation of each of these individual components, did a simple product, ignored the higher-ordered terms, and by matching terms we got the product rule back. Similarly, you can do the same thing for the chain rule. Let f of x equal g of h of x. Let us say you want f prime of 0. We will first approximate f of x by the linear approximation of g around h of 0. That means that g of h of x is approximately g of h of 0 plus h prime of 0 times x. But to get there, we first approximate h around 0. H of x is approximately equal to h of 0 plus h prime of 0 times x. So we have g of h of 0 plus h prime of 0 times x. Now we approximate this using a linear approximation of g around h of 0. That would be g of h of 0 plus g prime of h of 0 times the quantity h of 0 plus h prime of 0 x minus h of 0. The h of 0 terms cancel, and this essentially becomes g of h of 0 plus g prime of h of 0 times h prime of 0 times x. But we know that the linear approximation of f is f of 0 plus f prime of 0 times x. So this constant term is exactly f of 0, and that means that this coefficient must be equal to f prime of 0. By matching terms, we get f prime of 0 equals g prime of h of 0 times h prime of 0. Once again, this is not a surprise for anyone here. We have just derived the chain rule, which is one of the most basic rules. But you can get back the chain rule from the idea of linear approximations. Now we will do some simple examples for getting the derivatives. You could in principle just use the chain rule every time, but we will try to get it from the linear approximation approach. Let us say you've f of x equals e to the power 3x divided by the square root of 1 plus x. Call this f of x, and we want the linear approximation of this around x equal to 0. That means that we will pick x star equal to 0 and approximate this function around that point. You could just treat this as a single function and get the derivative using the chain rule. Then write f of x is approximately f of 0 plus x times f prime of 0. You could do that. Or you could do linear approximation from first principles and do each of these terms separately. E to the power 3x is approximately 1 plus 3x. The square root of 1 plus x in the denominator is 1 plus x to the power minus 1/2, whose linear approximation is 1 minus x over 2. Now multiply these. 1 plus 3x times 1 minus x over 2 gives a constant term, a linear term, and a quadratic term. The quadratic term you can ignore. If you do that, you get 1 plus 5 over 2 times x. You would have gotten the exact same answer if you had found the derivative of this function at x equal to 0, which would be 5 over 2. But it is also nicer to see that a more natural way of doing this is to take linear approximations of each of these components and work on it later. This is a direct application of the product rule and the chain rule as well. Now, let us say you want the linear approximation of e to the power of the square root of 1 plus x around x equal to 1. Just to give a variety here, we have always been doing x equal to 0. You could also do x around 1. You could once again just compute f of 1 and f prime of 1 and be done with it. You could do that just as well. And you could also just find the linear approximation of each of these terms around x equal to 1 and be done with it. Either way, what you would get is that e to the power of the square root of 1 plus x is approximately equal to e to the power of the square root of 2 plus e to the power of the square root of 2 divided by 2 times the square root of 2, all multiplied by x minus 1. Once again, whenever you're using the squiggly equal sign, which means approximately equal to, always give the conditions. This first one is around x equal to 0, and this second one is around x equal to 1. Linear approximations are really the key tool that allow you to get around most of machine learning with its very complex functions. You cannot really handle general functions. That is the reason why you do approximations. So finally, we move to the last application, which is regarding maxima, minima, and saddle points. This is something which you would have seen in your mathematics courses as well. You have your linear approximation of f around x star as f of x star plus f prime of x star times x minus x star. There is a very special case where you have f prime of x star equal to 0. Then your linear approximation L is actually not a function of x at all, but rather it is a constant. If f prime of x star is 0, then L sub x star of f is equal to f of x star. Even though the left-hand side is supposed to be a function of x, it is a constant. Such points, where f prime of x star is 0, are called critical points. These points are generally interesting in one way or the other. For example, in the case of one-dimensional functions from R to R, f prime of x star equal to 0 means that the point x star is either a maximum or a minimum, or what is called a saddle point. Let us write down the definition first. F prime of x star equal to 0 is the definition for the statement that x star is a critical point of f. If you have a point where f prime of x star is not 0, it is clear that the function is varying in the neighbourhood of x star. For example, if L sub x star of f at some point is equal to, say, 7 plus 3x, that does not matter much. But I am giving an example where, because L depends on x, what this says is that in the neighbourhood of x star, there is a dependence on x, which means that there is variation. But if you did not have a dependence on x at all, something like L sub x star of f is equal to 7, what this means is that around x star there is no variation. It is actually a constant. When can such a thing happen? Such a thing can happen only when x star is either a maximum, a minimum, or a saddle point. What do these terms mean? Here is an illustration of that. Visual description. There are 3 separate graphs shown on the slide, each with a coordinate plane and a blue curve representing a different function. In the first graph, the blue curve is a U-shaped parabola opening upward. The point x star is marked on the x-axis near the bottom of the U. At that point, the curve has a horizontal tangent line, meaning the slope is 0. The linear approximation at that point would be a horizontal straight line, a constant, touching the curve exactly at the bottom. This point is a local minimum. In the second graph, the blue curve is an upside-down U-shaped parabola opening downward. The point x star is marked on the x-axis near the top of the curve. Again, the tangent line at that point is horizontal, so the derivative is 0. The linear approximation is a constant horizontal line touching the curve at the peak. This point is a local maximum. In the third graph, the blue curve is shaped like a flattened S or a cubic-like curve. It comes up from the left, flattens out at a point in the middle, and then continues rising again. The point x star is marked at that flat spot in the middle. The tangent line there is also horizontal, so the derivative is 0. But this point is neither a maximum nor a minimum. It is a point where the curve flattens out and then continues in the same direction. This is called a saddle point. In higher dimensions, a saddle point really does look like a horse saddle. But even in one dimension, you can imagine this kind of looks like the back of a horse, hence the name. Critical points are particularly interesting for several functions, mainly because machine learning is really at its core just an applied optimization problem. You are interested in finding the minima or maxima of functions. And so we are really interested in finding points in the function where the gradient, or in one dimension the derivative, is 0. The derivative being 0 means that particular point is a critical point, and hence an interesting point. It can potentially be a minimum or a maximum. With that, we wrap up the univariate calculus part of the syllabus, and we will move on to multivariate calculus now.
Hello everyone, and welcome to another lecture of Machine Learning Foundations. We will continue with our calculus recap. We have been looking at univariate functions and univariate calculus, which is about functions f from R to R, where both the domain and codomain are R. Now we will generalize most of these ideas to multivariate functions, which are functions from R to the power d to R. The codomain is still R, meaning the output is still a real value, but the input domain is now d-dimensional. This brings us lots of intuitive geometric ideas for explaining multivariate calculus concepts. Still, we will be doing only mostly differential calculus, and most of these ideas you should have seen in your Mathematics for Data Science 2 course. Before we actually get into the calculus, we should first get the basic geometry of high-dimensional space. The basic sets for doing that are lines and planes. What is a line? We will be working with r to the power d now. A line in r to the power d is first of all a subset of r to the power d. A line is parameterized by two vectors. A line through the point u in r to the power d along the direction v in r to the power d is simply given by the set of all d-dimensional vectors x such that x can be written as u plus alpha times v, where alpha is any real number. We will see some examples soon, but the idea is pretty clear. A line through a point along a direction is given by this set. Sometimes you might also see another equivalent version, a line through 2 points, u and u dash. That is another definition. We will call this definition 2a and 2b. A line through the points u and u dash is simply given by the set of all x in r to the power d such that x can be written as u plus alpha times u dash minus u for alpha in the reals, which is also written as the set of all x in r to the power d such that x is equal to 1 minus alpha times u plus alpha times u dash for alpha in the reals. As you vary alpha, you get different points of the form 1 minus alpha times u plus alpha times u dash, and the union of every such element forms the line. You can see from this expression of the line to u and u dash that this is exactly the same as the line to u along the direction u dash minus u. Similarly, it is the same as the line to u dash along the direction u minus u dash. All of these three sets are really the same. The line to u and u dash is the same as the line to u along u dash minus u, and it is the same as the line to u dash along u minus u dash. All of these are the same subset of r to the power d. This is a simple exercise to prove. In fact, it is kind of obvious to see from this notation that u plus alpha times u dash minus u can just use u dash minus u as a vector indicating direction. If you do that, it is exactly the same. So a line is a subset of r to the power d, and it does look like a line. Now let us look at a visual example of a line. There is a coordinate plane shown with x1 and x2 axes. A blue line is drawn on this plane. The line passes through the point 1, 1, which is marked on the plane. The line extends in both directions along the direction given by the vector 1, 2. This means that from the point 1, 1, you can go in the direction of 1, 2, or in the opposite direction, and every point you reach is on the line. The set of all such points forms the blue line you see on the screen. You can see why it is called a line, because it really does look like a straight line when plotted. The next basic set in d-dimensional space is a hyperplane or just a plane. A hyperplane is typically a d-1 dimensional hyperplane. This is the default dimension of a hyperplane, and it is also a subset of r to the power d. We will say that your hyperplane normal to the vector w in r to the power d, with value b in r, is given by the set of all x in r to the power d such that w transpose x is equal to b, which is also the set of all x in r to the power d such that the sum from I equals 1 to d of wi times xi is equal to b. This is the definition of a hyperplane. There are other definitions as well, but those are slightly more complicated. This is the standard definition of a hyperplane, which is defined in terms of a vector normal to the plane and a value b. We will explain what these terms mean soon, but for now, this is parameterized by a vector w and a value b. Let us look at a visual example of a hyperplane. Imagine a three-dimensional space with three axes labeled x1, x2, and x3. The hyperplane we are considering is the set of all points where x1 plus x2 plus x3 equals 1. On the screen, you see a triangular plane floating in the 3D space. It passes through the points 1, 0, 0, 0, 1, 0, and 0, 0, 1. The plane extends beyond these points, but the visible part looks like a piece of paper cutting through the corner of a room. If you can imagine a 3D corner of your room and a piece of paper floating there at an angle, that is what this hyperplane looks like. This particular hyperplane is normal to the vector 1, 1, 1. What does that mean? If you imagine a ray originating at the origin, which is 0, 0, 0, and going along the direction 1, 1, 1, that ray would pierce this plane at a 90-degree angle, or perpendicularly. That is the reason why this particular plane is said to be normal or perpendicular to the vector 1, 1, 1. Now we will make a distinction between points, vectors, and tuples. All of these are represented by elements of r to the power d. A tuple is simply what you would store in a programming language as a d-dimensional vector. Points and vectors are both represented as tuples, but they have different meanings. A point corresponds to a location, and a vector corresponds to a direction. You can say, for example, that you are in Chennai and you are going towards Bangalore. That is a valid statement. You can imagine a line to Chennai along the direction given by Bangalore minus Chennai. So that is an example of a line. Directions are essentially vectors, and points are locations. There is a difference, but both are represented by tuples in r to the power d. From context, you should be clear whether a tuple is used as a point or as a vector. For example, consider this statement: the point 0, 1, 0 lies on the hyperplane T, which is perpendicular to the vector 1, 1, 1. You can say this, and you would not be wrong. It is clear from context that 0, 1, 0 is used as a point, and 1, 1, is used as a vector. Why is that? Because 1, 1, as a point makes no sense in this context. You cannot be perpendicular to a point. You can be perpendicular to a vector. Similarly, a vector cannot lie on a plane. Only points can lie on a plane. But we will be using all of this interchangeably. From context, it will be clear whether a particular element in r to the power d is used as a point or as a vector. Algebraically, it should be very clear, but geometrically, you must understand whether a particular tuple is used as a vector or as a point. With that, I think that gives the basic geometry tools required for understanding multivariate functions. Now we can move on to the basic building block of multivariate calculus, which are partial derivatives and gradients. What is a partial derivative? You have seen this perhaps in your school already. Let us say you can imagine a function f from r squared to r. That is the simplest multivariate function you can think of, a two-dimensional function. For example, let f of x1, x2 equal x1 squared plus x2 squared. The partial derivative of a function with respect to one of its arguments means that you view the rest of the arguments as constants. If that is the case, this is still a one-dimensional function. If you fix the other variables, it becomes a one-dimensional function, and then you can take the derivative. That is what the partial derivative means. Let us write down the definition formally. The partial derivative of f with respect to x1, evaluated at a point v, is the limit as alpha approaches 0 of f of v plus alpha times the coordinate vector e1 minus f of v, all divided by alpha. For the two-dimensional case, this is f of v1 plus alpha, v2 minus f of v1, v2, divided by alpha. For the purposes of calculation of the partial derivative with respect to the first variable, the second variable is kept constant. It is viewed as a constant, not changing at all. Only the first variable is changing. Similarly, you can do the partial derivative with respect to the second variable as well. That would be the limit as alpha approaches 0 of f of v1, v2 plus alpha minus f of v1, v2, divided by alpha. In general, if you have a d-dimensional function, how would you do this? The partial derivative with respect to the ith argument, evaluated at v, is the limit as alpha approaches 0 of f of v plus alpha times ei minus f of v, divided by alpha. What is ei? It is simply the coordinate vector with the ith coordinate equal to 1 and the rest equal to 0. You can easily see that is what is happening here. To get the derivative with respect to the first variable, you just take v plus alpha times 1, 0. To get the derivative with respect to the second variable, you take v plus alpha times 0, 1. In general, if you have d variables and you want the partial derivative with respect to the ith variable, you take f of v plus alpha times ei, where ei is the d-dimensional vector that is 0 everywhere except for a single 1 in the ith position. This clearly generalizes the case of two variables that we have here. If you go back to the two-variable case for do f by do x1 evaluated at v, if the second variable is fixed at v2, f is just a function of the first variable around v1. In that case, this exactly reduces to the standard derivative expression. In general, however, this is the general expression for the partial derivative with respect to the ith argument. You just consider f of v plus alpha times ei minus f of v over alpha, and let the limit of alpha approach 0. So for a d-dimensional function, you can evaluate the partial derivative at a point v with respect to each of the several variables x1 through xd. That means that for a function f from r to the power d to r, for any given point v, you have these quantities, do f by do x1 evaluated at v, do f by do x2 evaluated at v, and so on, up to do f by do xd evaluated at v. You can imagine putting all of these into a row vector, and you can just call this do f by do x. Here, f is a function and x is a vector. So we can take a derivative of a function with respect to a vector. By that, we mean this particular vector where you package all your partial derivatives into one row vector. Often, you would also use a gradient, which is the gradient of f at v, and that is simply the transpose of that row vector. Why is that? Because the gradient is typically written as a column vector. But the derivative of f with respect to x, where x is a d-dimensional vector, is written as a row vector. Otherwise, it is the same thing. The gradient is also a collection of partial derivatives. It is the d-dimensional vector which collects all partial derivatives. Now we can take derivatives of some simple functions. Let us use the same function as before, f of x equals x1 squared plus x2 squared. Here, d equals 2. What is do f by do x1? That is simply 2 times x1. Do f by do x2 is simply 2 times x2. Evaluated at a point v, do f by do x1 at v is 2 times v1, and do f by do x2 at v is 2 times v2. So the gradient of f evaluated at v is a column vector given by 2v1, 2v2. Another example might be a function f from r cubed to r given by f of x equals x1 plus 2 times x2 plus 3 times x3. What is the gradient of f evaluated at some point v? That is a vector given by do f by do x1, do f by do x2, and do f by do x3. If you view x2 and x3 as constants, and take the derivative of f with respect to x1, you get simply 1. Similarly, if you take the derivative with respect to the second variable, x2, you get 2. For the third variable, you get 3. So the gradient happens to be a constant vector 1, 2, 3. This kind of function, where the gradient is a constant, is called a linear function. F of x equals x1 plus 2x2 plus 3x3 is linear in all its arguments, and that is the reason why the gradient is a constant. With that, I think we have seen the basic tools, the partial derivatives and gradients that are required for multivariate calculus. We will see some more applications of these gradients and partial derivatives soon, but we will wrap this video for now.
Hello, everyone, and welcome to another lecture on Machine Learning Foundations. In the last class, we introduced and defined partial derivatives and gradients. That is the first and standard interpretation of a gradient, which is a computational interpretation. It is a package containing all the components of the partial derivatives. You have the partial derivatives with respect to all variables, and you put them all together into one vector. That is the gradient. That is the computational interpretation. In today's lecture, we will take a look at the other interpretations of the gradient, which are more geometric and more intuitive in nature than the computational approach. The first of these is the linear approximation interpretation. We have already seen linear approximations for one-dimensional functions. If you have a function f from R to R, and you want to approximate this function f around x close to x star, this is what you would do. F of x is approximately equal to f of x star plus f prime of x star times x minus x star. This is what you've been doing for linear approximations. We denoted this term as the linear approximation of f around x star evaluated at x. And this is a valid approximation when x is close to x star. That is for one-dimensional functions. How can we do the same thing for functions from r to the power d to r? In other words, now imagine v is a vector, a d-dimensional vector, and x is in its neighbourhood. X is a d-dimensional vector and x is close to v. Now you want to be able to approximate f of x. I will give the answer first, and then give various interpretations of it. The answer is that f of x is approximately equal to f of v plus the gradient of f at v, transposed, times x minus v. You can see the similarities to the one-dimensional case. Here, f of x first has f of v, which corresponds to f of x star, and you have the gradient of f at v transpose x minus v, which corresponds to f prime of x star times x minus x star. We will break this down even further as f of v plus the sum over I equals 1 to d of the partial derivative of f with respect to xi, evaluated at the point v, multiplied by xi minus vi. I have just broken down the gradient into its components. We will denote this in a very similar way. We will call this the linear approximation of f around the point v evaluated at x. And when is this approximation valid? This approximation is valid around x approximately equal to v. When x is close to v, this is a valid approximation of f. Now we will give one interpretation or one possible interpretation of this linear approximation. The way we do that is by breaking it down into multiple one-dimensional functions. We will make life easier for ourselves and just consider a two-dimensional function. This easily extends to multi-dimensional functions as well, but we will do it for just a two-dimensional function. Let us say f from r squared to r. We want to approximate f of x1, x2 around the point v1, v2. We can view the second variable as a constant and the first variable as the variable that changes. So f of x1, v2 is approximately equal to f of v1, v2 plus the partial derivative of f with respect to x1, evaluated at v, times x1 minus v1. This is just a standard one-dimensional linear approximation. We are approximating the function f viewed as just a function of its first argument, that is f of y1, v2 is approximately equal to f of v1, v2, and we are using the partial derivative of f with respect to the first argument at v times y1 minus v1. We can change the notation a little bit more. We can write f of y1, v2 minus f of v1, v2 is approximately equal to the partial derivative of f with respect to x1 at v times y1 minus v1. You can do the same thing for the second argument also. That is f of v1, y2 minus f of v1, v2 is approximately equal to the partial derivative of f with respect to x2, which is the second argument, at v times y2 minus v2. Let us interpret these two approximations. What this says is, as I move from v1, v2 to y1, v2, that is, as I move along the first axis, v1 changes to y1 while v2 remains the same. The value of the function changes by the partial derivative of f with respect to x1 evaluated at v times y1 minus v1. Similarly, this second expression says that as I move from v1, v2 to v1, y2, the change is given by the partial derivative of f with respect to x2 evaluated at v times y2 minus v2. But what we are now interested in is what if both of them move simultaneously? What can I say about f of y1, y2 minus f of v1, v2? The simplest answer is, well, if one variable changes, this is the change. If another variable changes, that is the change. If both variables change, the change is simply given by the addition of these two changes, which is the partial derivative of f with respect to x1 at v times y1 minus v1 plus the partial derivative of f with respect to x2 at v times y2 minus v2. Or in other words, now we will write down the full linear approximation, which is f of y1, y2 is approximately equal to f of v1, v2 plus the partial derivative of f with respect to x1 evaluated at v times y1 minus v1 plus the partial derivative of f with respect to x2 evaluated at v times y2 minus v2. Here we are going to make our life easier and just call this the gradient of f at v transpose y minus v. This is exactly our linear approximation expression. Remember, that is the gradient of f of x is approximately f of v plus the gradient of f at v transpose x minus v. Or in other words, f of y is approximately equal to f of v plus the gradient of f at v transpose y minus vy, and x are just dummy variables. They do not really matter. Now here are a couple of examples to run through. We will take a simple example first. Let us consider the function f from r squared to r, which is f of x1, x2 equals x1 squared plus x2 squared. Now here is the question, approximate f around the point, let us say, 6, 2. So v is equal to 6, 2 in our case. What is f of v first? F of v is equal to 6 squared plus 2 squared, which is 36 plus 4, which is 40. What is the gradient of f at v? The gradient of f at v is 2 times v1, 2 times v2, which is 12, 4. This is because the gradient of f of x is 2 times x1, 2 times x2, so the gradient evaluated at v in this case is 2 times v1, 2 times v2, which is 12, 4. With this we can actually give the answer, which is f of x is approximately equal to 40 plus the gradient of f at v transposed, which is 12, 4, times x minus v, which is x1 minus 6, x2 minus 2. We can simplify this further and say 40 plus 12 times x1 minus 6 plus 4 times x2 minus 2, which would be 40 plus 12 x1 plus 4 x2 minus 72 minus 8. Which would be 12x1 plus 4x2 minus 40. This is the linear approximation of f, which is x1 squared plus x2 squared around the point 6, 2. This is particularly valid around what point? Well, x1, x2 is approximately 6, 2. When your vector x is in a neighbourhood of 6, 2, this is a valid approximation. Let us visualize this further. There is a slide showing two contour plots side by side. On the left, you have the contour plot of the original function f, which is f of x equals x1 squared plus x2 squared. The contours are circles centred at the origin, because the function is the sum of squares. The point 6, 2 is marked on this contour plot, and the contour passing through it has the value 40, which is a circle. On the right, you have the contour plot of the linear approximation L sub v of f, which we just derived as 12x1 plus 4x2 minus 40. Because this is a linear function, you can see that the contours are all straight lines, and they are equally spaced. A couple of things to note immediately. F of v evaluated at 6, 2 is exactly 40. On the left contour plot, the circle corresponding to value 40 passes through the point 6, 2. On the right contour plot, the line corresponding to value 40 also passes through the same point. So the linear approximation is exactly equal to the function value at the point of approximation. At other points, you do not know, but it is exactly equal at the point of approximation. There are other properties as well, but that is the first property you should keep in mind. The linear approximation does change with the point that you choose. If you want to approximate the function f around the point 6, 2, this is the linear approximation. But if you want to approximate the same function around a point, let us say minus 6, 2, the linear approximation changes. you still have that property that at the point, you have 40 here and 40 there. F of v is exactly equal to L sub v of f evaluated at v. At a general point x, this is not true. At a general point x, you only have approximation. F of x, if you change v to x, is not exactly equal. It is only approximately equal. And that is also true only when x is approximately equal to v. Only around x equal to v do we have this expression. So that is the linear approximation viewpoint. And the approximation is completely defined by the gradient. In the same way that we have a linear approximation viewpoint for one-dimensional functions and a tangent line viewpoint, we can have a very similar viewpoint here. You can use tangent planes as graphs. This is the tangent plane interpretation of the gradient. That is, if you have the graph of the linear approximation of f around the point v, that is the graph of L sub v of f, which is going to be a plane. Recall that the graph of a function f from r to the power d to r is a subset of r to the power d plus 1. There is a three-dimensional plot on the slide. The blue surface corresponds to the graph of f of x equals x1 squared plus x2 squared. It is a parabolic bowl opening upward. The point v is some point on the x1, x2 plane, and the corresponding point on the surface is marked. An orange plane is shown touching the blue surface at that exact point. This orange plane is the graph of the linear approximation of f around the point v. Because L sub v of f is a linear function, its graph is a plane. This plane is tangent to the graph of f at the point v, f of v. Here, v is a d-dimensional vector, and f of v is a scalar, so together this is a d plus 1-dimensional vector. You can see that this orange plane touches the blue surface at exactly one point, and that point is v, f of v. So that is the other interpretation. We have the linear approximation interpretation of the gradient, and then we have the tangent plane interpretation. The tangent plane is also given by the linear approximation, which in turn is given by the gradient. Next, we have the contour set interpretation. Here is the statement. The gradient of f evaluated at some point v is going to be perpendicular to the contour set or level set given by the set of x in R to the power d such that f of x equals f of v. For example, let us say you take the point minus 6, 2. The gradient of f at that point is simply minus 12, 4. On the contour plot, there's a black arrow starting at the point minus 6, 2. This arrow points in the direction of the gradient vector minus 12, 4. The length of the arrow does not matter, only the direction matters. You can see that this black arrow is almost perpendicular, and in fact exactly perpendicular, to the level set passing through that point. What is this level set? This level set is exactly equal to the set of all x in R to the power d such that f of x equals f of v, which is f of x equals 40. This is the level set corresponding to f of x equal to 40, which is a circle centred at the origin with radius the square root of 40. And you have the gradient of the function f at v, which is minus 12, 4, and it is perpendicular to that level set at that point. I am not going to prove this completely, but what I'm actually going to prove is a slightly different statement, which is quite obvious. The gradient of f at v is actually perpendicular to the set of x in R to the power d such that the linear approximation of f evaluated at x is equal to f of v. These two statements are not exactly the same, but they are actually the same under certain extra regularity assumptions. But this statement is very easy to prove. Why is that? Because the set on the right side is actually a plane. The linear approximation of f at x is a linear function of x, and planes have a perpendicular vector built into them. What is that? Well, we will evaluate this set. This set is simply the set of x in R to the power d such that f of v plus the gradient of f at v transpose x minus v is equal to f of v. We do some term moving around, and we get that this is the set of x in R to the power d such that the gradient of f at v transpose x is equal to the gradient of f at v transpose v. This is of the form of a plane, the set of x in R to the power d such that W transpose x equals B. If you have such a plane, you already know that the vector W is perpendicular to that plane, and you can see that this is exactly of that form, where the gradient of f at V corresponds to W. So the gradient of f at V is actually perpendicular to this plane, which we have now proved. So that is the other interpretation of the gradient. The gradient of a function at a point B is going to be perpendicular to the contour passing through the point. Next, we move to another useful application or interpretation of the gradient, which has to do with directional derivatives. What is the directional derivative? We will first give an English definition of the directional derivative. We will define the directional derivative of the function f at the point V along the direction u. Here, f is a function from R to the power d to R, and u and v are vectors in d-dimensional space. So u and v are elements of R to the power d. I'm going to read this as the directional derivative of the function f at the point V along the direction u. What is the definition of this? The definition is the limit as alpha approaches 0 of f of v plus alpha times u minus f of v divided by alpha. Let us try to interpret this expression. What this is saying is that we want to move from v along the direction u. You are at the point V and you want to move along the direction u, and you are trying to quantify the rate of change of the function as you move along the direction u. That is the directional derivative of f along u. How will we compute this thing? Here, you can use our linear approximations because alpha is going to approach 0. You can approximate f of v plus alpha u using linear approximations. That is, f of v plus alpha u is approximately equal to f of v plus the gradient of f at v transpose alpha times u. Then subtract f of v and divide by alpha. You can see that f of v cancels, and alpha also cancels. So you are left with the gradient of f at v transpose u. This is nice and particularly interesting because it says that to compute the directional derivative of the function along any direction, all that you need to do is to take the dot product of the direction with the gradient. This is particularly nice because in machine learning, in practice, you often want to minimize a function. Most approaches take an iterative approach where you are at the current iterate, let us say v, and you want to decide which direction to move. You're going to move to a new iterate from v to let us say v dash, but you want to decide which direction to go. A very natural notion is that you can choose to move in the direction which decreases the function the most, or increases the function the most if you want to maximize it. So the notion you are looking for is what direction to move so that you can increase or decrease the function the most. The directional derivative is a very important tool for doing that. Before we attack the question, however, we will take a slight detour to give a very basic inequality known as the Cauchy-Schwarz inequality, which is useful for controlling the inner product of two vectors, such as the gradient of f at v transpose u. What is that? Well, you have two vectors a and b, which are d-dimensional vectors. The components are a1, a2, and so on up to add, and similarly b1, b2 up to bd. You want to be able to control their inner product, a transpose b. What we can show is that a transpose b is upper bounded by the norm of a times the norm of b, and lower bounded by minus the norm of a times the norm of b. This norm is the standard Euclidean norm, which is the square root of the sum of the squares of the components. So a transpose b is upper bounded and lower bounded between these two terms. You also happen to know when this equality happens. There is a very clear characterization for that. This lower bound equality happens when it is equal to alpha times b, where alpha is a negative scalar. If you have a negative scalar alpha, and r is equal to alpha times b, then a transpose b is exactly equal to minus the norm of a times the norm of b. And the upper bound equality happens when r is equal to alpha b, but alpha is a positive scalar. So in other words, if you want to maximize the term a transpose b, you will choose r equal to alpha b with alpha greater than 0. Now this will lead us to the next question. You want to find the direction of steepest ascent. Let us say you are trying to maximize a function f. You are at a current iterate v, and you want to choose a direction u that maximizes the directional derivative. You want to maximize the rate of change of f as you move from v along u. In other words, you want to maximize the directional derivative du of f evaluated at v. Find u which maximizes this term. That is your goal. We will do this a little bit more formally now. A direction cannot have arbitrary length, so we will fix the direction to have unit norm. So find u in r to the power d such that the norm of u is equal to 1, and which maximizes the directional derivative of f evaluated at v. But we already know this is exactly equal to the gradient of f at v transpose u. So v is fixed. The current point is fixed. The only thing that is not fixed is the direction u along which we move. So you want to find a u which maximizes the gradient of f at v transpose u. And that is already given by the Cauchy-Schwarz inequality, which means that you should pick u to be a scalar multiple, a positive scalar multiple, of the gradient of f at v. And you already know that u is a unit norm vector, so the scalar alpha is simply going to be 1 divided by the norm of the gradient of f at v. This gives the other interpretation of the gradient. The gradient is simply the direction of steepest ascent. If you are at a point v and you want to move along the direction which increases the function the fastest, you would choose the gradient. So that is the other interpretation, which is the direction of steepest ascent. We can finally wrap this up by saying you are at a point v. You have a function f from r to the power d to r. You are at a point v in r to the power d. Now let us say you want to minimize this function. What are the valid directions such that f decreases? Or in other words, for what values of u can you say that the directional derivative of f along u evaluated at v is less than 0? That is, the gradient of f at v transpose u is less than 0. So the set of descent directions is simply the set of u in r to the power d such that the gradient of f at v transpose u is less than 0. This is another tool that you will need when you do optimization, the set of directions along which you can move so that the function value decreases from the current value. These are all descent directions. With that, we will wrap up the alternate gradient interpretations. There are some slightly advanced rules which I will briefly skim over. We will not go into great detail on these, because we will not be using most of them, but we will do them anyway. The same way that you did for functions f from r to r. You had linear approximations, and you also had higher order quadratic approximations. You can do a very similar thing for functions f from r to the power d to r as follows. You have a function f from r to the power d to r. The linear approximation is simply given by f of x approximately equal to f of v plus the gradient of f at v transpose x minus v. This is valid around x equal to v. This is the linear approximation. You can do a higher order approximation the same way that you did for one-dimensional functions, but this is a little bit more complicated. You can also say f of x is approximately equal to f of v plus. The first term looks the same, the gradient of f at v transpose x minus v. The second term, on the other hand, is 1/2 times x minus v transpose times the Hessian of f evaluated at v times x minus v. I will not go into great detail into expanding the second term, but it is analogous to the quadratic term that we had for one-dimensional functions. That is, you have f of x is exactly equal to the linear approximation plus an extra term. This extra term involves the Hessian, which is the matrix of second-order partial derivatives. The Hessian is a d by d matrix, and x minus v is a d by 1 vector, while x minus v transpose is a 1 by d vector. Together this forms a scalar. I will not go into great detail on this, but you might find that more advanced optimization algorithms use a quadratic approximation rather than the linear approximation. But in most of machine learning, you will be sticking to linear approximations, which is this first term. The same way that you had maxima, minima, and saddle points for one-dimensional functions based on the derivative, you have a very similar situation here with gradients and maxima, minima, and saddle points. That is, if f of x is minimized at some point v, then you have that the gradient of f at v is the 0 vector. But it is not true the other way around. The gradient of f at v equal to 0 does not mean that f of x is minimized at v. However, if your function is minimized at v, then the gradient of f at v is equal to 0. This is also true for maxima. So any point where the gradient of f at v equals 0, the set of v such that the gradient of f at v equals 0 is called critical points. Note, however, that the gradient is a vector, so this 0 here corresponds to the vector 0, not a scalar 0. For special classes of functions, critical points can be shown to be exactly equal to minima. But in general, critical points are not guaranteed to be minima or maxima. But in either case, critical points are interesting points to analyze. If you want to find the maxima or minima of a function, you can just restrict your attention to points which satisfy this condition. This is called the first-order necessary condition for optimality. You only focus your attention on critical points and check whether they can be candidate minima or maxima. This is another application of the gradient, where you set the gradient to 0 and find interesting points, which are critical points, and then check whether they satisfy your condition. With this, we will wrap up.
Hello and welcome to this tutorial on Week 2 contents of the Machine Learning Foundations course. In this tutorial, we will be solving some problems from the topics of linear approximation, higher order approximations, multivariate linear approximation, and directional derivatives. Let us start with linear approximation. It is also called linearization, or local linear approximation, or tangent line approximation as well. The idea behind linear approximation is that when we zoom in on a point on a nonlinear plot, it looks very similar to a straight line. So we can use the equation of the tangent line at a point, say A, to approximate the value of the function at other points that are near to this point A. Let us take a look at an illustration. There is a graph shown with a blue curve and a red straight line. The blue curve is the plot of the function sine of x. The red straight line is a tangent to this function at a point A, which is marked on the x-axis. The point of tangent C is labelled on the curve. The idea here is that we can use the equation of this straight line, this tangent line, to approximate the value of the function at points which are near to this point A. As long as we are near this point A, we will be able to approximate well, and the error will be small. You can see that near point A, the red line and the blue curve are very close to each other. But as we move away from this point A, the error increases, and we will not be able to approximate as well. The gap between the red line and the blue curve grows larger. So that is the main idea behind a linear approximation. We will approximate the value of the function, which is nonlinear, by using the equation of the tangent line at a given point A. All those points that are near to this point will give a good approximation, but not for the points which are far away from this point. Now getting back, what is the need for linear approximation? Firstly, linear functions are easier to work with. That is why approximation is an important process in engineering and experimental sciences. In scientific studies, for example, if you are building a model, then linear functions help in making those models simpler and make the calculations easier. The second use is we can use linear approximation to find the value of a function at certain points when the exact values are not known. As an example, let us say you do not have a calculator and you want to find out the value of, say, square root of 5. Now since you know the value of square root of 4, you can use it to compute the value of square root of 5. So that is a very basic example. We will take more examples in a while. This is the equation that we will be using to approximate a given function f of x. Let us say the linear approximation is represented by L of x. So the entities that we need would be the value of the function at point A, which is f of r, and the value of the slope of the function at point A, that is f prime of r. These are the two things that we would be needing. Now if you observe carefully, this is actually the equation of a straight line at the point a comma f of r. You see, this is the equation of a straight line which passes through the point x1, y1, and m is the slope of the straight line. Now if you replace x1, y1 by the point a comma f of r, Because the straight line is passing through the point A, we can replace x1, y1 by f of r, and the slope m can be replaced by f prime of r. So this is what we get, and this is indeed the equation of the linear approximation of the function f of x at point A. Now we will use this equation to solve some problems. Let us say we have to approximate the value of square root of 50. The first step is to find a point O, which is near to this point at which we need to find the value of the function. Here the function is of the form square root of x, and x is equal to 50 is what we need to find out. So we will find a point O which is near to this point x where we know the value already. As an example here, we know that square root of 49 is known, so we will use r is equal to 49 to approximate the value of the function f of x is equal to square root of x to compute f of x at x is equal to 50. So that is the objective. The first thing that we need is f prime of x. We compute f prime of x, and then we replace f of x, and f prime of x by r is equal to 49. These are the two things that we need. We would be putting these values in the equation, so we get the linear approximation of the function L of x is equal to f of 49 plus f prime of 49 times x minus 49. Because here a is equal to 49, we replace the appropriate values. This is the equation of the straight line that we get. You see, this is a linear function L of x, which we would be using to approximate the given function f of x is equal to square root of x. Looking at the plots, there is a graph shown with a blue curve and a red straight line. The blue curve represents the function f of x equals square root of x, which is a nonlinear curve that increases slowly. The red straight line is the tangent at the point where a is equal to 49. At the points near a equals 49, the red line is able to approximate the given function well. You can see that near x equals 49, the red line and the blue curve are almost on top of each other. So that is how we can use this straight line to compute the value of the function near 49. Let us see when we put x is equal to 50 into this equation. What is the value that we get? That is 7.071, which we get. Now if you see the exact value of square root of 50 up to 3 decimal places, that also comes out to be 7.071. So as you can see, this was a nonlinear function, and we used an equation of a straight line to compute the value of this function, and we are able to approximate it decently well up to 3 decimal places. So that is the main idea of linear approximation. Now let us see what happens when we use this equation to find the value of the function at points away from A. As an example, if you put x is equal to 100, which is too far away from this point A, the straight line would be giving us some value, but there would be a gap, as you can see, between the red line and the blue plot. That gap will be the difference between the actual value and the approximated value. When we use this equation for x equals 100, we get 10.64, but the actual value is 10. So we get some gap. That is because we are moving far away from this point A. Let us take a look at one more example. We need to approximate the value of e to the power 0.017. Here again we would see a value which is close to this value and is well known. As an example, e to the power 0 is known. So what we can do is we can form the function f of x to be of the form e to the power x, while putting the value of r is equal to 0. So we get f of x to be equal to e to the power x, and then what else we need is f prime of x, which is equal to e to the power x again. Now we replace f of x and f prime of x by x is equal to a, which is 0 here. So these are the two things that we get, and we put these values in the equation as usual, f over plus f prime over times x minus a. Now when we replace the values, the straight line equation that we get is 1 plus x. There is a graph shown with a blue curve and a red straight line. The blue curve represents the function e to the power x, and the red straight line is 1 plus x, which is the tangent at the point r equals 0. This plot represents how the straight line is approximating this function at the point r is equal to 0. You can see that from x equals roughly minus 0.5 to plus 0.5, this equation is able to approximate the function well. The red line and the blue curve are very close in that region. So what we need is e to the power 0.017. We replace x by 0.017 and we get 1.017. And when we see the actual value of e to the power 0.017, that is also the same, so we are able to approximate quite well up to 3 decimal places by using the equation of the straight line. Now again, if we go far away from this point 0, there would be some difference between the approximated value and the actual value. Let us say we put x is equal to 1. So L of 1 will give us 2, while the actual value is 2.718. So that is the gap that we obtain. That is because there is a difference between 0 and 1 as compared to the gap between 0 and 0.017. So if we stay near 0, we will be able to approximate well. Now let us see one more example on linear approximation. Here we are given f of x is equal to square root of x plus 4, and we need to find f of 6. So when we replace x by 6, we get square root of 10. So square root of 10 is what we have to compute. Now as usual, we would see a value close to square root of 10 which is already known, and that is square root of 9, which we know already. So square root of 9 makes to be equal to 5, right? So f of x is given and it becomes 5, and that is how we start. Then we compute f prime of x, which we need to get the approximation, and then we replace x by 5. Is equal to 5, so these are the two entities that we get. Then we replace these values in the equation of linear approximation, and this is what we get. So this is the straight line equation that we get, 3 plus x minus 5 divided by 6. This was a nonlinear function, and we get a linear function, the linear approximation represented by this red straight line. You see that this is able to approximate well in a local region. As long as we are near this point 5, we can use this equation. Now what we need to compute is f of 6, so we replace x by 6 and use this equation. Let us see what we get. What we get is 3.16666. And if you see what is the exact value of square root of 10, that is equal to 3.162. So we see there is some small amount of gap. It is exactly matching when we see up to 2 decimal places. But when we go beyond, there's some gap that we observe, and that is because there's a gap between 5 and 6. If you use this equation to compute values somewhere very near to 5, say 5.1 or 5.2, you would get a good approximation. Now the next topic is, can we make this approximation a little better? Now let us talk about higher order approximations. As you see, a nonlinear function was given, and we were always coming up with a linear straight line equation to approximate that function. When we go one step ahead, we can also come up with a quadratic approximation as compared to a linear approximation, or we can go even beyond and we get even higher order approximation. So that is also possible. Now let us take a look at the equation that we would require to obtain that. This is the linear approximation equation. We now add one more entity to this equation to get the quadratic approximation, where we need the value of f double prime over, and we will get a second degree term over here. Similarly, if we go beyond, we can get higher order approximations by adding more terms containing higher degree derivatives and higher degree terms. So we can go as far as we wish to get a little better approximation. Now what we will do is we will take the same problem that we took in the previous example, and we will apply a higher order approximation to that and see how much better approximation we are able to obtain. This is the same problem. Earlier, we had applied the linear approximation, and we obtained some value where there was a little gap between the actual and approximated value. So now we apply, say, a third order approximation here and see what we obtain. We put it to be equal to 5. Now instead of f prime of x, we also need higher order terms of the derivatives. Let us compute the approximation up to third order. So these are the 3 terms that we would be needing, and then we replace x by a. These are the terms that we would be putting in the formula. So the linear approximation L of x becomes f of 5 plus f prime of 5 multiplied by x minus 5 plus f double prime of 5 divided by 2 multiplied by x minus 5 squared plus f triple prime of 5 divided by 3 factorial multiplied by x minus 5 cubed. So we are computing up to third order approximation. So we stop here. And we replace all the values. And this is what we get. So this is the equation of the approximation. This is not a linear approximation. This is a higher order approximation. Now we will see how much better we get when we use this equation as compared to the linear equation that we used in the previous example. There is a graph shown with a blue curve and a red curve. The blue curve is as usual the function f of x equals square root of x plus 4. The red curve is now not a linear straight line. It is a third order function. It curves and follows the blue curve much more closely over a larger range than the linear approximation did. We see that this function is able to approximate the given function better in a further range. So where we compute the value of f of 6 by using this equation, we get a value of 3.1622. And this was the exact value of the function up to 4 decimal places as well. So we are able to match this value with the exact value by using a higher order approximation. Now let us move on to the next topic, multivariate linear approximation. So far the functions that we were dealing with had only one variable, but sometimes we deal with functions involving more number of variables. So how can we approximate those functions is what we will look at. This is just a generalization of that equation that we used earlier. Now here the function f contains two variables x and y. We need to find the linear approximation of the function in the vicinity of the point a comma b. That is equal to f of a comma b plus the partial derivative of f with respect to x evaluated at a comma b multiplied by x minus a plus the partial derivative of f with respect to y evaluated at a comma b multiplied by y minus b. You know that when we have to find the derivative of a function which involves more than one variable, what we actually compute are the partial derivatives. So that is what we are using here. Instead of the term f prime of x, what we use is the partial derivative of f with respect to x and the partial derivative of f with respect to y. So this was a linear approximation of a multivariate function. You can also go one step ahead, and you can get a higher order approximation of a multivariate function as well, as we did in the previous case. Now here, we will take some examples of linear approximation of multivariate functions. Here the function is x times e to the power xy. We need to find the linearization of this function at the point 1, 0, and then we will use that equation to approximate the value of the function f at the point 1.1, minus 0.1. Now 1.1, minus 0.1 is in the vicinity of the point 1, 0, so we can use the approximation equation to compute the value of this function here. So what are the terms that we need? We first need to compute the partial derivatives of the function with respect to x and y. So the partial derivative of f with respect to x is what we need, and the partial derivative of f with respect to y. And then here the point a comma b is equal to 1, 0, so we replace these values in the partial derivatives. So these are the two terms that we get. Now we need to replace these values in the equation of linear approximation. So f of 1, 0 plus the partial derivative of the f with respect to x at 1, 0 multiplied by x minus 1 plus the partial derivative of the f with respect to y at 1, 0 multiplied by y minus 0 equals a comma b is equal to 1, 0. So this is the equation, and we replace the values, and this is the linear equation that we get. So now what we need to compute is f of 1.1, minus 0.1. We replace the values in the x plus y equation, and what we get is 1. So this is the approximated value of the function at this point. Now let us see what is the exact value of the function that we compute. We find it to be 0.98542. So there's only a very little gap between the actual and approximated value, which means we were able to approximate decently well by using this equation. So that was about approximations. And now the topic that we look at is directional derivatives. You might already be familiar with partial derivatives. So what are partial derivatives? If there is a function f of x, y, then the partial derivative of f with respect to x, also called f sub x of x, y, or do f by do x of x, y, what is it that it actually represents? It represents the rate of change of the function f with respect to x by keeping y constant. Now what do you mean by keeping y constant? If you visualize, by keeping y constant, we are actually moving in a horizontal direction. We are finding the rate of change of the function in a horizontal direction. So this is the rate of change of f as we vary x by keeping y fixed. Similarly, if you look at the partial derivative of f with respect to y of x, y, that is equal to the rate of change of f with respect to y where we keep x constant. Now when we keep x constant, that actually means we are moving in a vertical direction. So that is what it is. But sometimes we might want to change both of these variables, and we would want to see what is the rate of change of the function f when we change both x and y. So we might want to find the rate of change of a function in a given direction. So that is what exactly is directional derivative. It is the rate of change of f if we allow both x and y to change simultaneously in some direction. This u is a unit vector that represents the direction in which we want to compute the derivative. Now let me give you a small example here. Assume there is a huge hill on which you are hiking, and there is a road spiralling around this hill which is making you reach the top of the hill. So while you are hiking along this road, at some point you want to know what is the slope of the hill along this road. That is what you might be interested in finding. Or in another scenario, you might throw some ball down the hill, and you might want to know the slope of the hill in that direction, in the direction where this ball goes. So these are two different directions. One is the direction where this ball goes downhill, and the second is the direction along which you are walking on this road. So these are two different directions. Standing at the same point, you are interested in finding the slope in two different directions. So that is one scenario where directional derivatives might be useful. So let us see how we compute them. They are indeed the weighted sum of partial derivatives. So this is the partial derivatives, and this u vector is giving you the direction in which you want to compute the directional derivatives. So this is what you get, which is actually a weighted sum of the partial derivatives. Let us take an example. You are given a function f of x, y, and you want to compute the derivative of this function in the direction of a vector that is given to you. So the terms that we need to compute this are firstly the partial derivatives, do f by do x, and do f by do y. Now secondly, we need a unit vector in the direction in which we want to compute the directional derivative. So this is not a unit vector, so we will first convert it into a unit vector by dividing each component by the magnitude of this vector. Next we compute the directional derivative as a weighted sum of the partial derivatives. So this is what we get. That is how we compute the directional derivatives. We will take one more example and we will conclude. Here in this problem, we are given a function and we are given a direction, and we are also given a point at which we want to compute the directional derivative. So as usual, first we will compute the partial derivatives, do f by do x and do f by do y. Now for the direction. We are already given a unit vector, so we do not need to convert it into any other form. So to compute the directional derivative, we find the weighted sum of the partial derivatives. So this is what we get as the directional derivative of the function in this direction. Now we have to compute it at a given point 2, minus 3. So we replace x and y by this point, and this is what we get. So this is the rate of change of the function when we move 0.6 in the x direction and 0.8 in the y direction. So that is what it precisely represents. So this is how you can compute how much a function varies in a given direction at any point. So that is going to be a very useful concept which we might be using in future. Okay, so these were some of the example problems on the topics that were covered in the lecture. I hope you were able to understand. Thank you.